Right. In this chapter, chapter 17, I'll talk about Serial Peripheral Interface (SPI), which is one of the most used peripheral interfacing in embedded systems. So outline is as follow. I'll start talking about the SPI architecture, how it's organized, and so on. Then how AVR is dealing with SPI, the pins in the AVR, and so on. Um, the control status and data registers in the AVR for SPI protocol and slave select treatment and how we can configure SPI for master and slave configurations in AVR. And we will have a simple example about 7-segment display drivers. Okay, so SPI, it's serial peripheral interface as an expanded how we read it is a interface bus, and it's incorporating into many devices like analog to digital converters, digital to analog converters, EEPROMs, and so on. And they're actually doing full duplex 3-wire transfers. They have master and slave operations. You can see how it is organized inside of a microcontroller. They have a interrupt flags, write collision flag, and wake up from idle mode, and so on, which are some specific features of the SPI. And they have a different modes, and we will examine the pins of the SPI bus and show how to read and write operations in the SPIs are working. So SPI originally started by Motorola Corporation, and now it's on Freescale. And in recent years, it's becomes widely used as a standard adopted by many semiconductor chip companies. And SPI actually uses 2 pins for data transfer, which we call them STI. STI is the serial data transfer. Serial data in, and we have got STO where we use it as serial data out. Now it's promising because instead of using 8 or more pins in the traditional buses, we just use 2 pins. And this reduction of data pins, it's actually reduces the package size and also the power consumption drastically. So SPI bus also has the shift clock pin in order to synchronize the data transfer between the 2 chips. And the last pin of the SPI bus is the chip enable, which we know as a CE, which is used to initiate and terminate the data transfer. So in total, we have got 4 pins: SDI, SDO, SCK or SCLK, and chip enable or chip select, whatever you want to call it. But generally we use it as chip enable. So it's a 4-wire SPI interface. Now, in many chips nowadays, the SDI, SDO, CK, and CE signals are alternatively named as, we'll see, MISO, master out, slave in, master in, slave out, SCK, the clock, and SS, which is slave select. Okay, so these are the names that we are using. And there's also widely used standard, which we call it a 3-wire interface bus. And in the 3-wire interface bus, there are only SCK, chip enable, and only single pin for the data transfer. Okay, And the 4-wire bus can become a 3-wire interface when the SDI and SDO data pins are tied together. So how SPI works, I want to talk about that, how it is working. So you can see a simple shift registers over there, which are 8-bit long, and it means that after the 8 clock pulses, the contents of the two shift registers are going to be interchanged. So the master is going to send out from master master out slave in, and then it's also going to receive it from master in slave out. Okay, so you can see how the shift register is operating. You can see that whenever the SPI clock generator is ticking for 8 clocks, the master out slave in is going in, and then from the slave to the master in slave out is going to be shifted. Okay. And when master wants to send a byte of data, it places the byte in its shift register and generate 8 clock pulses. So after the 8 clock pulses, the byte is transmitted to the other shift register, which is the slave shift register. And when master wants to receive a byte of data, the slave side should place the byte in its shift register, and after 8 clock pulses, the data will be received by the master shift register. And it must be noted that the SPI is a full duplex. So what do we mean? It sends and receives the data at the same time, as we have seen it in the USART. So, so this is how we can configure it. Master can connect it to the number of slave devices. So their mesos has to be connected, MOSIS has to be connected, common SCK and slave select pins over there from master into the separate slaves. And AVR is using 3 or 4 pins over here, as you can see. PB0, PB1, PB2, and PB3, slave select, the clock, MOSI, and MISO. Now, generally, microcontrollers are in the master mode, okay? They are not in the slave mode. Or if you have maybe 2 or 3 microcontrollers on the same board or on the same chip, then you can think about configuring it as a slave. Because, and we need to be very big careful over here. So when we are connecting a device and SPI to a microcontroller, we use microcontroller as the master while the SPI device acts as a slave. So SPI interface has no control on the slave select. So we have to control it from the software side. So if you are configuring the port as an output port, then this part is for the PB0 pin only. There's no problem. It's just serving the general output functions. You can send out data. But if it's going to be configured as an input, you must set this to be staying high all the time. Otherwise, it will enter to the slave mode. Okay, so when it is 0, it's going to be in slave mode. We need to be careful. So in our course and in this chapter, we are going to use SPI in the master mode. And one another important thing, so the SPI protocol uses the clock to synchronize the transfer of information 1 bit at a time, where the MSB goes in first. And during the transfer, the chip enable must stay high. And then the information, like the address and the data, is transferred between the microcontroller and the SPI device in groups of 8 bits, where the address byte is followed immediately by the data byte. And another important thing is in order to distinguish between the read and the write operations, the D7 bit of the address byte is always 1 for write, and for the read, D7 bit is low. So there are a couple of registers in AVR that is used for SPI operations. And one of them is the SPI control register, where we have got interrupt enable pin or bit, SPI enable. So we have to set it if you want to use SPI interface. If you want to use interrupts, you have to set this. And data order, LSB is transmitted first, and so on if you want to. And master or slave select. Then we need to set this as we are a microcontroller to be in the master mode. The clock polarity and clock phase is other two important because in SPI communication, the master and slaves must agree on the clock polarity and the phase with respect to the data. So the Freescale names these two options as CPOL and CPHA respectively. And most of the semiconductor companies are using these conventions. So there are two important things about the clock polarities. So when the CPOL is 0, now SCK is low in the idle, and when it is 1, SCK is high in idle. And the phases, so with the phase, if the phase is 0, it samples the data on the first clock edge, but if the phase is 1, it samples the data on the second clock edge. So you can see how these are going to be configured. So from here, as you can see, CPOL is 0, CPHA is 0, okay? So that means we have got the SCK low in idle, and where, as you can see, when CPH is 0, the data is sampled on the first edge, okay? And when CPHA is 1, okay, so data is sampled on the second edge, not the first one. And when CPOL is 1, as you can see, it's high in idle. And again, data is going to be sampled because CPHA is 0 on the first edge. And when CPH is 1, it's going to be sampled on the second edge. And CPOL is 1. So this is how it is operated. And also we have the scalers again here with the SPI as well. If you want to scale down the clock for 16, 64, 128, 832, and 64 configurations can be found on it. Now, another important register is the status register, which shows the interrupt flag. So it's set, when it is set, the serial transfer is completed, or it may be switched to slave mode. And write collision is another one. So if SPDR is written during a receive transfer, SPDR is the data register. So when it is receiving something and it's written, so it's going to be a write collision to the different data at the same place. And another bit is the last bit, which is the least significant one, which is the clock rate. So if it's set, it doubles the clock rate in the master mode. And SPDR is a data register where we hold the data. So 8-bit register, and we clock it, and it's like a shift register. So SS pin is the slave select pin, as I already mentioned. Now, in the master mode, you can set this pin direction to output, and SPI will not control the pin. But if you set the direction to an input, then you have to pull it up. it should be high. If you make it externally low, the SPI module will stop working in the master mode and it will change to the slave mode, okay, which is going to clear this master bit over here. So slave mode, if you have multiple microcontrollers and you want to use one of those as in the slave mode, so SS pin is always input and you cannot control it by the software. You should hold it externally low to activate the SPI. And when SS is driven high, SPI is disabled and all pins of SPI are becoming inputs. Okay. And master operating mode. Now, there are various steps in order to operate the microcontroller in the master operating mode. So what we need to do, first we have to set the master operating mode to be 1. Okay, we have to set the frequency of the clock by setting the values over here. And then data order, if not set, it is 0. So we're just using MSB to LSB. And we need to enable the SPI by setting the SPE bit. Then we write a byte to the SPI data register where we want to shift it out. Then we check if the data transfer is finished. And when it changes to 1, or you can use an interrupt if you don't want to use a poll, we just read the received byte from the data register before the next byte arrives. And after the transmission, the byte in the master shift register is moved to the slave shift register, and the byte in the slave register is going to be moved into the master shift register. So it's actually happening at the same time. And if you just want to read the data, you can just send a dump or dummy byte or the bulk byte and then read the received data. And if you are going to operate in the slave operating mode, so we have to set the SPI data order, enable SPI, then write byte to the SPI data register. Again, check if you want to use interrupt, you can use interrupts and read the received byte from the data register. So SPI can also perform single and multi-write operations. So you can use it as a single mode, as I already mentioned, by clocking for 8 bits and you're sending out an 8-bit address and then the data and so on. And if it's going to be operating in the multi-byte mode, then burst of data bytes can be transmitted after the address with an so address is going to be incremented internally, and you are just sending 8 clock pulses, 1 packet, 8 clock pulses, another packet, 8 clock pulses, another packet, and so on. So this can also be possible with the multi-byte mode if you want to send burst of data bytes. So reading or writing doesn't matter. It's actually happening in the same manner. So if you are reading, then master out, slave in, you send out the address, then master in, slave out, you read the data. And if it's in the multi-byte mode, again, you send the with the address in 8 clocks, and then you read the data, burst of data. So there's nothing different with the single byte or multi-byte mode. You just need to know that you can configure it and you can do that. So 7 segment, it's made up of 7 LEDs to show different numbers. Probably you're all familiar with this. You can display the decimal points. And there are 2 types of 7 segments, common anode and the common cathode. So as you can see, there has got a common ground, and the anode is the tails, and the cathode is the heads of the LEDs. So as you can see, the cathode path is commonly grounded. This is what we are using in these 7 segments. And in many applications, you need to connect 2 or more 7-segment LEDs to a microcontroller. For example, you want to connect 4 7-segment LEDs directly to a microcontroller, and you need 4 times 8, 32 pins, which is not feasible. So what we can do is we can use these max 7921 connections. So it's a driver actually. So it's an SPI driver, and which you can connect 8 7-segments to this driver, and you can, as you can see, AVR driver is in between, and you can just control different 7-segments over here. So the data packet format is as follow. It's 16 bits long. The first byte are the command control bits. So D15 to D12 are the command byte and are don't cares. And then D11 to D8 are used to identify the meaning of the data byte to be followed. And the second byte, which is D7 to D0, the 2 byte is called the data byte. So first, you should make CS low, the chip select, before transmitting. Then you transmit 2 bytes of data and terminate the transmission by making again the chip select high. So this is just show it on the diagram over here. And the data packet format is shown here. You don't need to memorize anything over here. You just need to know how it is going to be operated. If you want to set a value of digit 0, then you just use this command X0001. Or if you want to set decoding mode, then you use X1001, which is X9. Scan limits, turn on and off the displays, and so on and so on. So these are important if you want to operate multiple 7-segment displays. And when we talk about set decoding mode, there are 2 modes if decoding mode is off and on. And enabling decoding is useful when you do not want to deal with the converting a binary number to 7-segment codes manually. And the bypassing is useful when you want to show a special character or any other thing that is not predefined. Okay, so as you can see, we have got the don't care command bits and the data bit of each command. So if the decoding mode is off, we set the value of digit X command to turn on and off each bit of segment. And if you want to turn off a segment, you should write 1 or 0 to its bits. It's a typical thing. And each bit of the data bit is assigned to the 7 segments. So like you can see it over here. Okay, so this will activate one of those. And if decoding mode is on, and you just set the value of digit X, command to display the BCD value, and command 3, set the value of digit 2 and the third digit to 5. So then command 3 is activated. Okay, so digit 2 is, as you can see, is X3. Okay, and data bits are going to be 5. So 0, 0, 0, 0, 1, 0, 1. So this is how we use this. And I have got an example over here. So it's asked as what sequence of bytes should be sent to MAX7 221 in order to enable the decoding function for digit 0 and digit 2 and disable the decoding function for other digits. Now, the first byte should be XXX, okay, as we are going to use the decoding function for digit 0. Then we start with XXX, I'll write capitals. Then as we are going to activate decoding, we need 9, okay, so 1001. And then we need to have the data bits. Now, the data bits for digit 0 and digit 2, that means first four are going to be zeros, then 0, digit 2 is 1, digit 1 is 0, and digit 0 has to be 1. So decoding function for digit 0 and digit 2 can be configured like that. Digit 0 and digit 2 has to be activated for decoding, and the rest are disabled. Okay, so we are just using a decoding for that. And then it says, after running the above example, what sequence of numbers should be sent to MAX7221 in order to write 5 on digit 2? Now, as we have activated decoding, then all we need to do is, if we go back from the table, for the digit 2, we need to have hex 3. So then we have got X, and then we have got 0011, which is 3, and then the data bits. So we have to write 5. So the first four is 0 again, and then 0101, 5 as the data now on digit 2. So digit 2, then we will have 5 as a data. So it's pretty straightforward. There's nothing really difficult over there. We'll do also an example to demonstrate how this is going to work. Now, how do we use MAX7221 programming in AVR? We have to initialize the SPI to operate in master mode, including the pin configurations, enable or disable the decoding mode. If you want to have a decoding, then you need to do X9. Set the scan limit, default is 0. Set the intensity of light if you want for the LEDs. And turn on the display and set value of each digit. So example is given over here. Write an AVRC program to display 57 on the 7 segment with clock division of 16 and use 7 segment decoder for the 2 digits used. Okay, so we need to display 57 over here. Okay, and there will be a clock division of 16. So let's write this together as a C program. Now, it's good to define some of these things, and it's a good practice. I'm trying to find the hash now. Okay, so include AVR io.h, and then I want to define these. Define MOSI, which is going to be 2. Define SCK as 1, and define slave select as 0. We are actually defining the pins over here, okay, which I'm going to use in order to activate it. So then we have got the int main void, and let's start writing the code. Now, as these are in DDR B, port B, I have to use to activate it. So 1 for MOSI, master out slave in pin. Then one for SCK, and then one for slave select. So this is actually going to tell us that MOSI and SEK are outputs. Then we need to specify what SPCR, the control register, is going to be configured as. So this one. And we have to enable SPI. Then we have to enable the master mode. And then we have to enable the SPR0 for the order. So enable SPI master. Then, so what we need to do is enable decoding for digit 1 and 2. We just need to say execute 0 hex 09. Okay. And for digits 1 and 2, then 0B I'll just do this. And 0011. So we can say enable decoding for digits 1 and 2. And then we can say execute 0 hex 0B and 0 hex 02. Which are going to scan to 7 segments. Then we have to execute 0 hex 0C, 0 hex 01, and that's going to be turn on the chip. So 0 is off, and 1 is on. And then execute once again on digit 1, it's going to be 07. So display 7 and execute 0 hex 2, digit 2, it's going to be 0 hex 05. And display 5. Then while 1, return 0. Then we close brackets. So that's how we can operate it. Then we have to define the execute over here. So void execute. That's going to be unsigned char comment and unsigned char data. And so we can say port B and we called one slave select, initializing the packet. There should be a filter over here. Nope. It's difficult to find the tilde now. Anyway, I'll carry on. And that's going to be initializing the packet. And then SPDR is going to be the command that we want to send. So we can say start command transmission, and then while we are doing a polling here to check if the data transfer is done, SPSR and one for SPIF to check the flag. And wait transfer finish. So then SPDR equals data, start data transmission, and then while it's one SPSR and one for SPIF. Once again, wait for transfer to finish. And then port B, one, terminate the packet. So slave select for termination. And that's it. So this command is going to execute and send out the commands and the packets together. So you can see how these are going to be executed, and you can find the similar coding over here with the comments. So when you compare SPI and UART or USART, which you have seen it, and USART is using multiple, SPI using a duplex, so sending and receiving at the same time. SPI is synchronous, USART can be async or sync. 2 wires are used in USART, 4 wires depending on the number of slaves. The speed is 25 megabits. For USART is 20. Flow control, acknowledge pins, no acknowledgement needed. Energy consumption, very low energy, medium energy. Communication distance is around 15 meters and 20 centimeters and so on. And these are the architectures inside of the AVR which are serving these 2 protocols. So that's all I want to say for SPIs. As I said, they are quite important in embedded systems. So please do read these and follow these carefully. And if you have any questions, feel free to ask. Thank you.